Just in case.
All right, so the following speaker is Ignacio Rozada, and the title of his talk is Stop Waiting for Quantum, Disrupting Combinatorial Optimization with Analog Hardware Today. So thank you very much, and please go on.
Thank you very much. Thank you very much, David, for organizing this lovely event. Apologies for the provocative title. Anyway, let's see if I can live up to the... but I debated whether changing it, but I think Natalia's highlight of the questions driving the Eisen community and how do we show to the world that we're there and that we can do practical, valuable things, I think are very important. I want to start by just every so often I look at combinatorial optimization and it sort of blows my mind just how in all of these talks we talked about 100, 1,000 variable problems, and just the solution spaces are so huge. And the problems are not, we don't just do gradient descent. We have very rugged landscapes, and then still somehow we find solutions, things work. And this is not only something that happens here in academia, but really the world is surrounded by these traveling salesman problems, and we get on Uber taxis and flights arrive more or less in time. So the world works having to deal with all of these NP-hard, very tricky problems. Anyway, this makes me very happy. Okay, this work is part of something called a quick collaboration. This was a grant competition started by DARPA. It just finished its phase 1. Our particular entry into this competition is a collaboration between HPE, 1QBit, Jülich in Germany, and UC Santa Barbara. And the idea was my team brings the, let's say, the algorithms benchmarking expertise, and the other groups are all very well versed in Memristor. So we built a Memristor solution for this competition. And what I want to point out is that the spirit of this competition is to build hardware solvers, quantum-inspired classical computing. So they specifically are veering away from quantum computing, but very much in the spirit of solving problems as energy efficiently as possible. The key metric that we're measured for is, I think in one word, energy to solution. So how much energy do you need to find a solution with 99% guarantee? I think I showed this slide on Wednesday. Again, the motivation for this is that we're surrounded by optimization problems. Despite all the hype around AI, which definitely has its place, there are very, very many high-value problems that are from the very, very large, very complicated problems where people throw huge amounts of compute to ones that require very energy efficient, very small solvers that are very limited in budget and time, in energy and time. And yet this is something that we all carry phones and they rely on these types of algorithms. I'm going to spend probably the majority of my talk on one example problem. It's called the quadratic assignment problem. To me, this is like the pistachio problem. When you go to a new gelato place, I always try first pistachio flavor just to see if if that works, then it's probably a good gelato place. So to me, QAP has been always my reference problem to try on new hardware. I've been very lucky a few years ago to try many different Ising solvers. It's not a good problem to try on an Ising machine, at least it wasn't. But I think it makes for a very good test case. First of all, it's a very well-known problem. It's from the 50s. It has a number of high-value applications. It's a simple problem where the question is you have a fixed number of sites and a fixed number of facilities, and you want to assign the facilities to the sites such that the flow between each pair of facilities is minimized. You can imagine how this maps to chip design. There's also a number of warehousing applications that directly, it's exactly the QAP. This is papers from last year from groups in Amazon and the usual suspects. And the key part of the QAP to me is that the problems of around 50 instances are not probably optimally solvable. So it's a very hard problem. Like almost every instance is typically hard. You cannot throw it into Groby, or exact solvers generally do very poorly. So it's potentially a good fit for hardware QUBO solvers. The problem is quadratic. Again, small problems are hard. And the heuristics that you need, the state-of-the-art heuristics to solve it are very simple. Simulating, annealing, taboo, swapping solutions similar to, it's very related to traveling salesman problem for the people that work on it. And the state-of-the-art in CMOS classical applications, because of all of the applications, there's a lot of work around it, and there's GPU, but there's very fast GPU and FPGA implementations. I wouldn't be surprised if there are already ASIC implementations. I'll get to those in a second. And as I said, it's a very simple problem. You have, in this case, the A and the B matrix represent the facilities and the locations. And this essentially, in this formulation, a solution is a permutation of the place where the facilities, let's say 0, 1, 2, 3, and 4. We're putting facility 2 in the first location, facility 0 in the second location, etc. There is an alternative formulation, which is, I think, a little bit more implementable, or if you want to implement, you can implement it in one line in Python or MATLAB or whatever, where you represent the permutations as a permutation matrix, and then you only have these 4 or 3 matrix multiplications, and this gives you the evaluation. So you have a very simple evaluator. It's expensive because it's all matrix multiplications. But you can build heuristics on top of it that can be either in the first permutation formulation to swap the place of 2 facilities, or in the second in this middle permutation matrix scenario, you swap rows or columns of the matrix to get a new feasible solution. And there is an extension of the permutation matrix scenario where you simply take the A and the B matrix and take the Kronecker product of them, and the permutation matrix you extend it into an array. And this is also, if you evaluate these Kronecker products on both sides, you can immediately see that if the Kronecker of B and A, you write it as a Q, and it looks exactly like a QUBO problem. And that's exactly what it is. So it has a very, very natural QUBO representation. And going back to the previous talk, the tricky thing is that the solution vector X is made of one hot encoding terms. So in order to have feasible solutions, your solutions have to represent permutations. And so there are a number of downsides to the QUBO formulation, and this is what's always made it very tricky when I've tested it on ISIM solvers. First of all, this, let's say quadratization to bring it into the binary formulation blows up the solution space. So you go from n factorial space in the permutation sense to 2 to the n squared solution space in some sense. And it's not that there's suddenly like a lot more solutions, but all of these new solutions are infeasible. So it becomes a very, very needle in the haystack problem. Where not only do you have more solutions, but your original feasible solutions, and I'll explain it in a second, typically become local mini-mined in this new formulation of the problem. And what happens to solve it with a QUBO system, normally what you do is you add this Lagrangian term that penalizes the infeasible solutions. And this has the effect of, if you think of, let's say this is, you can see my mouse, right? So this is a 3-facility QAP problem. In the binary space, you represent it as this 9 binary vector. In order to go to another feasible solution, you have to perform 4-bit flips to arrive at another feasible solution. It cannot be any 4-bit flips, obviously. You have to satisfy the 100 encoding constraints. And when you put this system into a heuristic, this is like in my experience, the worst possible scenario. These figures that I stole from probably the fastest paper that I've seen show that in the native space you have a problem that it's already hard, but you can go from feasible solution S1 to solution S5 by permuting something to something where you're in solution S1. Let's say you start there, and in order to get to solution S5, you have to go uphill. You have to do 3 uphill moves and then somehow find your way on the other side. And typically what happens is really that you get stuck in invisible space and you get lost. This is a simulation that I made here where I compared a simple taboo. For people that are familiar, a taboo is a very simple heuristic where every solution that you see, you ban it for a little bit so that you don't go back to this known solution. A taboo heuristic in blue is able to find the optimal solution here a couple of times. And I also implemented a taboo with this cubo formulation. And there were only a handful of feasible solutions that it was able to see. And they were all in having distance very far away from the optimal solution. And in fact, I implemented also, it's very simple to generate random permutations. So you can think of the most basic QAP solver could be just generating random permutations. And generally, this random permutation solver does better equivalently to this Cubo taboo solver. We tested it on, this can be more or less generalized a little bit more. There's been a fair bit of work on this field trying to solve QAP with D-Wave and a bunch of other icing machines with predictable. You can imagine the results based on what I just said. And I want to show this is, I think, to me, the final result of, I think, the most effort that I've ever seen put into solving QAP in its Cubo formulation. This is from a work by Masoud Mohseni, which probably some of you know. He's a collaborator in my group. So when he was at Google, he developed these very sophisticated parallel tempering based on local Monte Carlo algorithms. And then he threw them with like Google resources, plus a very sophisticated hyperparameter optimizer. And the best that they could get to was 14% residual on, this is, so far is a 40 variable problem, 1600 binary variables. I mean, to be fair, this is beyond what any of the other Cubo QAP solvers had achieved. But if I have my own QAP solver based on in its natural formulation. Just throwing this problem into this simulated annealing, path relinking, population annealing, parallel tempering. With default parameters, in 1 second or less, you find a much better solution. And if you tweak the parameters a little bit, you can find the optimal solution for this problem on any of these solvers running on a laptop. So lessons learned here, these, as presented earlier, the 100 counting of assignments means that feasible configurations are separated by at least 3-bit flips, which in practice really becomes a lot more than 3-bit flips. And then any notion of moving between neighboring feasible states and following a gradient becomes lost because of having to go through these all up and down paths. And moreover, if you're trying this on an annealing type solver, this becomes much, much worse because as you quench the temperature, doing uphill moves becomes more expensive or harder, and you just get stuck on local optima. And there's a caveat though. You could possibly avoid all of this in feasible space within this binary space by performing multiple flip moves. And I'm going to detail what we did, and this is we didn't give up on let's say binary or Cubo solvers, but we found out that every time you're in a QO solution and you flip one of the variables at random, this in some sense forces the other 3-bit flips that you need to do to go back to a feasible solution on this side. And if you analyze it mathematically, I'm not going to go through the details here, but you can come up with a formula that, given any solution, you can immediately find in a very cheap way what are the 4 bits that you need to do to go back to another feasible solution, and in some sense remain in the feasible space, avoid all of these huge infeasible configurations. Beyond, even I think more nicer than that is that you can not only find the one random move that gets you to another feasible solution, but you can very easily find all the n choose 2 moves that define the full, let's say the one swap neighborhood for QAP. And this is something that you see in most of the state-of-the-art solvers. Evaluate the full neighborhood in FPGAs or GPUs, evaluate the solutions on all of these neighborhoods, and then choose one of these solutions to guide that. So we can do that efficiently. And then given that we have all of these neighborhoods, you can put it on a nice heuristic, similarity annealing, parallel tempering, taboo, or even just a greedy heuristic. And the other nice thing that we found out is that once you're in your new place, in this case X6, and you need to regenerate the full neighborhood again for your next move, a fair bit of that neighborhood is going to be shared by the original neighborhood. Instead of n choose 2, you only need to recalculate order n moves. So it becomes much more efficient than regenerating the neighborhood at each iteration. So where does this leave us right now? Just to give you an idea of what the state of the art is right now, at least as of 2 years ago, the state of the art solution was a parallel tempering based FPGA implementation where they can find the energy to solution for about 100 variable problems, ranges between 1 to 100 joules. I like energy to solution, by the way, because this is not something that you can, so you're free to throw as many resources and try as many computers or solvers in parallel, but you have to report the energy for all of these. So this sort of, I think, levels the field. And in this particular case, with their FPGA, they get down to very low energy to solution. And to be fair, I think it's fair to assume that there's probably an ASIC solution out there, and we are aiming to beat something that is at least 10 times better than this FPGA paper. And also to give another where we want to go with this, industrial warehousing applications are in the order of 300 variables. This is not something where you need to prove that you find a solution. The goal is to find a reasonable solution so that they can use and that they can generate relatively fast to guide their stacking robots and things like that. This is a problem that we proposed within the quick program, as each team was able to propose their own problem. Plus, DARPA specified a few other industrial problems to solve. In a particular case, we haven't. We've been taking steps towards being able to solve this problem on our hardware. There's a few things that we're not there yet. One of them is we need to distribute the problems in their binary formulation become very large, and we have a distributed architecture. So this is something that we have to implement for QAP. Keeping track of all of these multiple neighborhoods requires additional hardware than what we have right now for the applications that I'm going to discuss in a second. And QAP also requires some level of precision. So we've been doing analysis on quantization for optimization, which for some reason there's not so much literature out there. We should be able to, we're planning on publishing something relatively soon, but QAP luckily doesn't seem to be very sensitive to even 4 to 6 bits quantization. Okay, so now I want to introduce this is the hardware that we built for this quick collaboration. In principle, we want to run or get it to the point where we can hopefully soon solve QAP there and prove that we can beat the state of the art. For now, what we did with we call it Klima. It's a K-local in-memory accelerator. From the get-go, we decided not to build an icing solver, which was a little bit different from the majority of the other teams participating in this competition. We decided to aim for a specific problem application, and in this case, DARPA suggests SAT was one of the prescribed applications, so we went for a SAT solver. And our architecture is really these two blocks. That is the red square is an evaluator. It's based on something called content addressable memory. It's sort of like the dual of RAM. You specify a pattern, and it tells you if this pattern, for example, a solution, is this solution already in your array. So you can use that to, in parallel, evaluate solutions on in the SAT case on all of the clauses that you're evaluating. And the other block is the blue square. The W square is a gradient evaluator where in one iteration it can do a full gradient evaluation. In the sense that given a solution, it tells you if you flip each of the variables, what's going to be the contribution to improving or worsening the solution. So you can do the full gradient evaluation, and then if one possible heuristic is you can add a little bit of noise to all of the gradients that you calculate, and then choose the best one. Or you can implement, one thing that we've done is that you can also natively implement some of the state-of-the-art heuristics that people use for SAT. And I have to say that makes it very convenient for us when benchmarking applications, because you have, if your hardware is implementing exactly a well-known heuristic, it becomes very simple to simulate. The first results that we have in the literature are the ones just above. We compared 3 SAT and 4 SAT problems. I think an important thing to note about Klima that I should make more emphasis on, Klima is natively high order. So if you have k variables, you can have up to order k interactions. SAT problems don't really come very often in beyond order 8 or 9. But it certainly becomes useful in some other applications. It's also, there's a very nice connection with Cuba or Puba problems. And you can use Klima also natively as a Puba solver, again, for k-local problems. The version that we're showing here implements 64 variables and 256 clauses, and there's some very improved results coming up in the Hot Chips conference in August. These tiles are very small. The memristor logic that is implemented here is very dense. So each tile is essentially less than 1 millimeter squared. So we've been thinking of how to distribute problems with these tiles. So we have a paper on something called a field programmable icing array, which is a way of tiling our tiles in order to tackle larger problems. Another application that I discussed on Wednesday is that we follow the guiding principle of trying to build solvers that map as close as possible to applications. We realized that a number of the SAT problems that we were tackling, or a number of applications that people typically solve with SAT solvers, originally come from applications that have XOR clauses. One of the most standard applications, almost everything in cryptography has XOR secrets in them. And SAT solvers have become more or less the default way to attack or to test the hardness of cryptographic problems. And we realized that our hardware had support for evaluating XOR clauses. I don't want to get, I'm running a little bit out of time, but the short story is that we realized that simply adding support for XOR clauses within our hardware and keeping the exact same heuristics without doing anything different with XOR clauses versus CNF clauses gave us about a 10 to 100x advantage over the mapping the problems to CNF and solving them with a CNF solver. We were a little bit skeptical of this. We thought maybe CNF SAT solvers are very advanced, and it's possible that we could get the same gains if we run the problems through a preprocessor. And indeed, these originally XOR problems that become CNF have significant gains when you preprocess them before solving them with a SAT solver. But interestingly, this is more or less perpendicular to the gains that you see with the XNF solver. If you preprocess a problem and then convert it back to XNF, you see another 10x advantage that compounds on top of this. This being run on the same tile that we use for CNF, it's scalable when using the FPIA fabric. And I'm going to discuss in a second that given that we have a lot of small tiles, we've been investigating parallel tempering applications on this hardware. Here this is just some results. We compared it with the state-of-the-art SAT solvers on CNF and also the two SAT solvers that are natively also XNF capable, one called CryptoMinisat and XNF solver. And in general, we saw significant advantages, especially in energy to solution. And finally, just to wrap this up, I wanted to say that our hardware, because of the memory that we use, annealing type algorithms are a little bit tricky to implement, especially changing the noise parameter at each iteration. It's not the end of the world, but we came to realize that it was much easier to take a number of tiles, have a solver run on them with a fixed noise parameter or a temperature parameter if you want, and then use the ideas behind parallel tempering to build a compounded solver that gave us a better solution. It's a little bit of a generalized parallel tempering solver because the SAT solvers are not really MCMC-based heuristics, so you don't have accept and reject mechanisms. But it turned out that it worked out nicely. We were able to using the same heuristic and comparing it with the parallel tempering version. And we're not reporting also we're not only looking at the time or the energy on one of the replicas, but we're looking at the energy for the whole ensemble of replicas that are built into the parallel tempering implementation. And taking everything into account, we still do better, and in some cases significantly better than walked solver. And in particular, we noticed that parallel tempering is particularly useful for very hard problems, which makes sense. Like you wouldn't want to use something too sophisticated. Like easy problems you can solve locally with almost any heuristic. We compared it also with replicas that don't have the intercommunication the replica exchange mechanism that parallel tempering has. We didn't see a huge advantage on parallel tempering, but it was significant. It was definitely better. This is still we bought this in PR applied earlier this year, and this is something we're still looking into. And just to wrap this up, the nice thing about this parallel tempering implementation is that when we implement it in hardware, we realized that it's only a 1% increase in overhead versus what we had just with the replicas. So for this very small overhead increase, you get a significant gain. Thank you very much.
Thank you very much for your very nice talk. Is there any question? Yes.
Very nice. Enjoyed the talk. So you mentioned, I think, that the highest order of the polynomial you can go to was 8 or 9%.
No, if we have k variables, we can go to order k.
The higher order of monomial and more pupil problem.
It's defined by the number of variables. I was saying that the SAT problems typically don't have very high order.
Yes.
Right.
Yeah.
You can map it to three, but there's a usual, it's like cubo to cubo. You can map things to three sets, but you have more clauses and more variables, and the landscape also.
That general polynomial optimization problem.
Right.
So what is the highest order that polynomial that you can have? Are there any limitations on the degree of this polynomial?
In principle, there's no limitations. So if you have k variables, you can go up to order k.
Variables, I mean the order.
I mean, you could have a term that multiplies all of the variables together, and this would be native. Mhm. Yeah.
So this will just come down to just having enough, in your scheme that you showed, you need to have enough layers. Is that what defines how high you will go and how configurable is that? This is my question. Before.
Let me, sorry. I don't have a lot of details here. So each row of this crossbar array encodes in the SAT sense encodes the variables that appear in one. Each row encodes one clause on SAT. So if K31, K32, and K33 are in that one clause, they'll show up there. When in the Pubo version is that each row is going to be one product term from the Pubo. So if you have ones in all of the terms, it'll be represent a term where all the variables get multiplied together.
The question? Can I quickly ask, so what is the role of the nodes and how can we control it in your engine?
That's a very good question. In the case of SAT, is very nice because it's binary, so we don't really. It's very easy to control noise with SAT. On QAP, not so much because you have different weights. So there's our group has published a number of papers on how you can correct for noise. There's a trade-off between the number of circuits the number of circuits that you need to add in order to, if you need 8 bits or 10 bits or 12 bits of precision. The reverse of that is that the current hardware that we have right now, most of our energy budget goes to the random number generator because we are using, I think, an XOR shift or something like that. But the plan is to, at some point, use the intrinsic noise from the hardware, either temperature or voltage noise, to drive the annealing mechanisms.
Okay, thank you very much. Okay, so